All right, let's get into a story that is, and I mean this literally, out of this world. We're going on a full-blown cosmic detective mission, but we're not hunting for clues in some dark alley. We're hunting for them inside a rock that fell from the sky. And our suspects? Well, they're stars that died billions of years ago.
Just let that sink in for a second. It sounds like something from a movie, right? To actually hold a physical piece of stardust from a sun that blinked out of existence long before our own solar system even got started.
But here's the thing, it's not science fiction. Not at all. Inside a famous meteorite that fell in Murchison, Australia, scientists found these tiny, tiny grains of dust that were forged in the atmospheres of ancient stars. I mean, this is the real deal. Actual pre-solar material. Stuff that was around before our sun was even a twinkle in the galaxy's eye.
So the big question is, how on earth did they do it? This is the story of the hunt for what are called pre-solar grains. And you can think of them as tiny, perfect time capsules that somehow survived the fiery birth of our solar system, only to be trapped inside this rock for billions of years.
Now, you have to understand, not all meteorites are the same. The Murchison meteorite specifically is a type known as a primitive chondrite. The best way to think about it is like a cosmic fossil. It's an incredibly old, totally unaltered piece of the early solar system. It basically acted like a vault, a cosmic safety deposit box, perfectly preserving this ancient stardust that was just floating around in the giant cloud that eventually became, well, everything we know. Okay, so that brings us to a huge problem. Finding these grains, it's just monumentally difficult. They're unbelievably small, and they're all mixed up with the regular, boring rock of the meteorite. So our detectives needed a way to spot the alien in the crowd. They needed a fingerprint.
And that fingerprint has a very cool name, an isotopic anomaly. Here's how to think about it. You know how every element, like carbon or silicon, can come in slightly different weights? Those are called isotopes. Well, our entire solar system was mixed together like a giant cake batter. So everything in it, Earth, Mars, you, me, we all have the exact same, very consistent ratio of those isotopes. But a grain from another star? Nope. It was baked in a completely different cosmic oven. It has a totally weird alien isotopic recipe. And what's so wild is just how loud these fingerprints are. The scientists were looking for rare gases like xenon and neon, which get trapped inside the stardust as it forms. And the isotopic ratios they found weren't just a little bit different. Some were up to 1,000 times different from our solar system standard. That's not a clue. That's a giant, flashing neon sign screaming, "I'm not from around here," and pointing directly to really exotic origins like exploding supernovae or ancient carbon stars.
Okay, so they knew what to look for, but actually getting their hands on those tiny grains, that required an absolutely epic feat of chemistry. I mean, this wasn't something they just figured out over a weekend. It was a brutal, decade-long mission to invent a way to isolate these microscopic survivors. They basically designed what you can only call a chemical gauntlet. It was a process of elimination. First, they used incredibly powerful acids to dissolve away 99% of the meteorite, all the normal rock, gone. Then they used these harsh oxidizers to destroy all the organic carbon that formed inside our solar system. Poof. After that, they had to carefully separate out the different survivors, like tiny diamonds. And then finally, after even more acid baths, they isolated their prime targets, pure silicon carbide and graphite. It was a process of just systematic destruction, all to find the few things that were literally indestructible. And this quote right here just perfectly sums up scientific discovery. The researchers themselves, back in 1994, said the procedure is now fairly straightforward. I just love that. Straightforward. You know, after you spend 10 years of your life perfecting it, it's just an amazing testament to the kind of patience and grit it takes to really push the boundaries of what we know. So, after all that blood, sweat, and acid, how much stardust did they actually find? Well, for silicon carbide, one of their main targets, the final haul was about 6 parts per million. 6! That is an unbelievably small amount. To put that in perspective, that's like searching through 1,000,000 grains of sand on a beach to find just 6 of them that glow in the dark. That's the scale of what they accomplished. So, the detectives finally have their evidence. It was incredibly hard to get, but they have it. Now it's time to put that evidence on trial. What secrets could these impossibly tiny grains possibly be holding? You know, one of the biggest questions they wanted to answer was actually about the size of the grains. It sounds almost too simple, right? But the size distribution of cosmic dust held the key to a huge debate raging in astronomy. What does stardust actually look like right when it's born, fresh from its parent star?
So there were basically two competing ideas. On one side, you've got the power law theory. This comes from what astronomers see when they point their telescopes out into space. And it predicts that dust grains are kind of like shattered glass. The smaller the piece, the more of them you'll find, meaning there should be a nearly infinite number of tiny, tiny grains. But what the scientists actually found in the meteorite was a log normal distribution. Think of a classic bell curve. Most of the grains were clustered around an average size with very few tiny or very few large ones.
And right here, this is the smoking gun. If that power law theory was right, and there really were tons of those tiny grains out there, then the scientists should have found a huge amount of silicon carbide in the meteorite. The theory predicted they'd find about 87 parts per million, but what did they actually find? Only about 7 parts per million. That isn't just a small difference, that's a massive, gaping hole in the theory. The conclusion was just inescapable. That huge population of super tiny dust grains that the power law theory depended on, it just wasn't there. Not in this pristine, unaltered sample from the very dawn of our solar system. So, what was the final verdict from our Stardust detectives? What did this incredible piece of evidence really mean for how we understand stars, dust, and, well, the entire galaxy? The first part of the verdict is this. Stardust is born looking exactly like the grains they found in the meteorite. When it first condenses in a star's atmosphere, it just naturally forms in this classic bell curve log normal size distribution. The meteorite, it turns out, preserved the baby pictures of stardust. And the second part solves the whole mystery. So why do astronomers see something totally different? Because over millions and millions of years, floating through the galaxy, that original dust gets beat up. It gets battered, fragmented, and broken down by shock waves and radiation. It gets reprocessed. And that leads us to this amazing conclusion. We're really looking at a tale of two different kinds of dust. The grains inside the Murchison meteorite are the original, factory fresh product, straight from the star. The dust that astronomers see with their telescopes, that's the weathered, processed stuff that's been through eons of cosmic wear and tear. And because of this incredible detective work, we can now study both. For the first time, we can actually see what stars produce before the harshness of interstellar space changes it forever. It really makes you wonder, doesn't it? For decades, the answer to this huge cosmic question was just sitting there, locked away inside a rock. It just took 10 years of brilliant, painstaking work to build the key. So what else is out there, hiding in plain sight, just waiting for the next generation of cosmic detectives to come along and crack the case?